In this presentation, we will show a novel graph-based GUI presentation that facilitates the understanding of GUI structure. Prior research has mostly focused on constraint-based and deep learning-based methods. The former, however, requires designers to define or select constraints or patterns, while the latter often provides final results directly to the designers but offers less control over the design process. Our goal was to propose a suitable GUI representation enabling deep learning models to predict constraints. This enhances the network's ability to establish connections and deepen its comprehension of both element properties and constraints. Different GUI representations can capture various factors of GUI design, and the choice of data representation for GUIs can significantly impact the capabilities of downstream tasks within graphical user interfaces. Some work has focused exclusively on textual content in GUIs, but has neglected the visual aspects of design and the variety of GUI elements. In contrast, other approaches have emphasized visual appearance and GUI element types, but have overlooked the content of the elements. This results in similar treatment for GUIs that share structural and visual similarities, but differ in content. To our knowledge, no prior deep learning-based method has considered layout constraints in GUI representation. Layout constraints represent the layout relationships between GUI elements, such as alignment, same size, and grouping. Most existing methods, which employ convolutional neural networks to learn GUI images, face challenges because they must learn layout constraints from pixels. This makes training a model to predict constraints challenging. To address this gap, we propose a novel graph-based GUI representation, Graph4GUI, that integrates GUI elements with layout constraints. Our approach is to represent relatively universal principles of layouts as constraints in a graph, thus reducing the need to learn them from scratch. We formulate a bipartite graph to express GUI elements and their relationships via two kinds of nodes, element and constraint nodes. Each GUI element node represents various element properties, including visual appearance, textual content, element type, position, and size. Constraint nodes include four types of constraints: alignment, same size, element grouping, and multimodal grouping constraints. We then utilize graph neural networks to learn a domain-specific representation from the graph structure data. It can capture the visual, spatial, and semantic factors of GUIs and enhance the performance of downstream GUI tasks, such as GUI autocompletion, GUI topic classification, and GUI retrieval. We demonstrate the capability of Graph4GUI with the GUI autocompletion task due to its complexity. This autocompletion problem is challenging, not only because exploring potential GUI element combinations is computationally costly, but also because good solutions must consider visual, spatial, and semantic constraints among the to-be-placed elements and those already present. Given a partial UI, we construct a heterogeneous bipartite graph that covers both GUI element properties and layout constraints. We create an element node for each GUI element, which expresses properties specific to individual GUI elements. We also create a constraint node for each layout constraint associated with GUI elements. For instance, if elements 2, 3, and 4 are left-aligned, we create a constraint node specifically for the left alignment. The element nodes 2, 3, and 4 are connected to this constraint node, indicating that these three elements are left-aligned. Similarly, we connect all the element nodes to their corresponding constraint nodes. Integrating element properties and layout constraints into a single unified graph facilitates a comprehensive representation of a GUI's elements and layout. When presented with an unplaced target element, our objective is to predict its size, position, and the associated constraints it should adhere to. We input both the graph representing the partial GUI and the element node for the target element into the graph neural networks. As we progress through the layers of the graph neural network, each node iteratively gathers information from its associated constraint nodes and other element nodes. The model is then capable of predicting the edges between the target element node and constraint nodes, indicating which constraints should be satisfied by the target element. Subsequently, we can compute the position and size of the target element based on the predicted constraints. By iteratively predicting the sizes and locations of yet unplaced elements, we can support designers by auto-completing partially completed GUI designs. We demonstrate Graph4GUI used in an auto-completion task as a plugin in Figma, a GUI popular design tool. The plugin offers GUI element prediction suggestions with confidence levels, helping designers prioritize element selection. It also features a preview window that shows a prediction preview of the element placed on the GUI when hovering over an element, providing an intuitive view to help decision-making. After selecting a GUI element, the plugin can automatically place it in the suggested position and size on the canvas. Our method enables the iterative prediction of unplaced GUI elements. If you are satisfied with the position and size of the element shown in the preview window, you can proceed to double-click on the GUI element to place it on the canvas. In summary, compared to other data-driven approaches, our graph-based representation enhances the understanding of GUI structure, thus improving the explainability of the model. This capability allows our representation to effectively execute various downstream GUI tasks.